In this lesson, we're going to take a look at concavity and points of inflection. So by the end of this lesson, we want to know what is meant by the concavity of a curve, what exactly are points of inflections, and we want to be able to use an interval table in the second derivative to find the points of inflection and the intervals of concavity for a curve. So what is concavity? Well, a curve, or part of a curve, can be said to be either concave up or concave down. And you've encountered these words back in grade 10 when they were talking about parabolas. If a parabola was said to be concave up, it opened up like this. And if it was concave down, it opened down like that. Now we can apply that same sort of concept to part of a curve. A curve can be concave up if it kind of looks like this, where we're just sort of taking the right-hand part of that parabola, or if it does something like that, where we're just sort of taking the left-hand curve. Same thing with concave down. A curve that is concave down could also look like this, or could also look like that. So what do we mean? Well, concave up. In grade 10, we said that the curve, quote unquote, opens up, okay, when we were talking about a parabola. But in this course, we want to look at what is happening to the slope of the tangent to the curve. So if I pick this curve right here and I draw a series of tangents to it, as I go from left to right, I notice that the slope of the tangent that I draw to my curve is increasing. Those tangent lines are getting steeper. So I can say that the slope of the tangent to the curve is increasing. Again, as I go from left to right along my graph. Well, if the slope of the tangent is increasing, what tells us the slope of the tangent? Our first derivative. So our first derivative, f prime at x, is increasing. What tells us how our first derivative changes? Well, for any function, if we're interested in the change in that function, we look at the derivative of that function. So if we're interested in the change in the first derivative, we want to take a look at the second derivative. So if our first derivative is increasing, our second derivative must be greater than 0. So our curve is concave up if our second derivative is positive. So how can we remember that? Well, we can imagine we're looking at our second derivative. If it's positive, our curve is concave up. What about concave down? Well, we can make the same kind of argument for concave down. I can pick my concave down curve, and I can draw a series of tangents at various points, and I notice that the slope of the tangent is decreasing. So concave down means our curve, quote unquote, opens down. Another way of saying that is the slope of the tangent is decreasing. What describes the slope of the tangent? Well, our first derivative. So our first derivative is decreasing. What describes the change in our first derivative? Our second derivative. So if our first derivative is decreasing, our second derivative must be less than 0 or negative. So if our second derivative here is negative, our curve is concave down. So that's concavity. Okay? A curve can be concave up, concave down. Now this doesn't have to apply to the entire curve. We can just have part of a curve being concave up and part of a curve being concave down, which means that over the course of its graph, the concavity of a single function can change from being concave up to concave down, or concave down to concave up. And the points where that occurs are called points of inflection. So a point of inflection is a point on the curve where the concavity changes. So we could have a function which is concave up and then switches at a point to being concave down. Let's label this. This is concave up. Over here it is concave down. So this point right here where it changes is called a point of inflection. Similarly, we could have something that, I don't know, looks like this, okay, and a point right in the middle. Over here, this side here, our curve is concave up. Over here, our curve is concave down. So our point of inflection is right there in the middle. Okay. Now, how do we recognize a point of inflection? Well, if we look at our first example again, if our curve is concave up, then our second derivative is greater than 0. If our curve is concave down, our second derivative is less than 0. So what happens right at that point where it changes from where the second derivative changes from being positive to being negative? Well, it's got to equal 0 right at the middle. So our second derivative will equal 0 at a point of inflection. Okay. So let's just write that out. So points of inflection occur where f double primed at x equals 0. Now, just because the second derivative equals 0 at a point doesn't mean there's necessarily a point of inflection there. Okay? So you always want to check to make sure that the concavity actually changes on either side of that point that you're interested in to verify that it is in fact a point of inflection. Okay? Other places where your concavity can change are at vertical asymptotes and other weird looking things. So if we're looking for points of inflection, we're also going to consider cases where the second derivative does not exist. Okay? Now, points of back when we did the first derivative test, we said that local maximum and minima occur where the first derivative equals 0. Okay? But a first derivative equals 0 didn't mean that there was actually a local maximum or minimum. Because one of the other things that can happen where the first derivative is equal to 0 is you can have a point of inflection. So we might add another little note down here. First derivative can also equal 0 sometimes. So f prime of x equals 0. So let's rewrite that. Sometimes the first derivative is equal to 0 at a point of inflection. Not always, but sometimes. So what do you need to be able to do with all of this? Well, here's an example of the kind of question you need to be able to do. Determine the intervals of concavity and the points of inflection for this function. F at x equals x over x squared plus 1. And first thing we're going to need is our first derivative and then our second derivative. If we're going to find those possible points of inflection, we have to set our second derivative equal to 0. So our first derivative would be this. Then we would go ahead and take the second derivative of that. And we'll have negative 2x, 3 minus x squared, all over x squared plus 1 cubed. So let's look for, if we're looking for points of inflection, okay, we are going to look for where our second derivative is equal to 0, or where our second derivative does not exist, because those are the possible points where our concavity can change. And we're going to use these points like we use our critical numbers with our first derivative test. They're going to define the intervals where we check the concavity. So where does the second derivative equal 0? Well, it's going to equal 0 where the numerator of our second derivative is equal to 0. So let's set our numerator equal to 0. 2x 3 minus x squared equals 0. This is already factored for us, so we want to take each of these factors and set it equal to 0. So negative 2x equals 0, and 3 minus x squared equals 0. Here we get the solution x equals 0. 3 minus x squared equals 0. Well, let's bring the x squared over to the other side. 3 equals x squared. That gives us solutions of positive minus root 3. Okay, we get two solutions because x could be positive root 3 or x could be negative root 3. Where is our second derivative not going to exist? Well, there we want to check cases where the denominator of our second derivative is equal to 0. So we'll have x squared plus 1 all cubed equals 0. And let's see. That whole left side is going to equal 0 where x squared plus 1 equals 0. If we were going to solve this, we would get x squared equals negative 1, and there's no solution here. If we were to take the square root of both sides, we would be taking the square root of a negative number, which has no real solutions. And we're only interested in real solutions here. So we have 1, 2, 3 numbers that we can use to define our intervals. So that's what we're going to use these for, to define our intervals. And we're going to set up an interval table. So our intervals are going to go from negative infinity to negative root 3, from negative root 3 to 0, from 0 to positive root 3, and then from positive root 3 all the way up to positive infinity. And it's kind of helpful when you're doing this to sometimes evaluate these roots. So root 3 is 1.73 approximately. So just sort of keep that in the back of your mind when you're maybe picking a test value in each of these intervals here. So what are we doing with this interval table? We are checking the concavity of our curve in each one of these intervals. So we want to check the sign of each term in our second derivative. So we have a negative 2x and a 3 minus x squared in the numerator, and we have an x squared plus 1 all cubed in the denominator. So fill in our table here a little bit. And what are we doing with this? We are checking the sign of our second derivative. And remember, we're looking for information that this tells us about the original function. So f at x. So our first term, negative 2x. Well, that is going to be positive where x is negative, and negative where x is positive. 3 minus x squared. If I imagine putting in a large negative number, if I square it, I get a large positive number, so that's going to give me something negative. But if I put in something like negative 1, and I square it, I'll get positive 1. 3 minus 1 is going to be something positive. So it's going to be positive for values close to 0, and negative for large positive or negative values. My third term here, no matter what I put in there, when I square it, I'll get something positive. I add 1 to it, it's still positive. I cube it, it's still positive. So this is positive always. So my second derivative is going to be negative, then positive, then negative, and then positive. So what does that tell me about my original function? Well, if my second derivative is negative, my curve is going to be concave down, then concave up. Second derivative is negative again, concave down, positive again, concave up. So I have 3 points of inflection. Where my curve changes from concave down to concave up. So I can figure out the coordinates of those. Those are going to be negative root 3 over 4, 0, 0, and root 3 over 4. So I've got my intervals of concavity, and I've got 3 points of inflections. And if we're worried about this, we can always verify this by taking a look at the graph. This is what the graph of the function would look like. You can see I've got a point of inflection right here at 0, 0. My curve, if I'm going towards positive values here, we can see it's concave down, but right about here, it switches to being concave up. If I start at 0 and go the opposite direction, I see that it's concave up until we get right about there, and then it switches to concave down.